Today on Macaulay Math, exponential functions and the natural number e. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 1 on exponential functions. Our goals for today: we're going to recognize and evaluate exponential functions. We're going to graph exponential functions. We're going to recognize and evaluate exponential functions of base e, and then we're going to use exponential functions to model data and predict future events. This lesson introduces exponential functions and Euler's number e, often called the natural number. It will look at how to graph and transform exponential functions, as well as how to use exponential functions to model data and use that data to make predictions.
All right, so we will start with the general exponential function, and that's going to be f of x is equal ab to the x. And so here is our first example of a function where the independent variable is an exponent. We're going to call b the base, we're going to call x the exponent, we're going to call a the coefficient. The general shape of the graph of any exponential function where a and b are both positive, it's going to look something like this, where it goes through your y-axis at a, and that's fairly straightforward because any value that crosses the y-axis has an x value of 0, and if I plug 0 in, I get b to the 0 is 1. 1 times a is always going to be a, and a is the y-intercept, and b is going to affect the shape of the graph. The bigger that b is, the more pronounced the curve is. The closer to 1 that b is, the more gradual that shape is. And we can see that real quick with a real quick Desmos demonstration. So here we have f of x is equal ab to the x, and I have a slider for a and b. If you change a, it changes the y-intercept, and you can see that it corresponds. When I plug in 4, I get 4. And then the shape is changed by changing b, and so the bigger b gets, the steeper that curve becomes, and the closer to 1 b gets, the gentler that slope is. Okay, so on this next slide we have our general exponential functions and then some specific use exponential functions. And so our general function f of x equals ab to the x, and that is our general exponential function. We have 3, and we won't use all of these today, but I thought I'd put them all together in the notes so you have them together. Our simple interest equation is a equals p times 1 plus r to the t. In this instance, here is our f of x, here is our a. The 1 plus r represents b, and t is the x value. A compound interest formula, a equals p times the quantity 1 plus r over n all to the nt. And then the continuous growth function, which I'm going to call the PERT function, is a equals pe to the rt. We'll talk about e here in a moment. In each of these instances, p is always going to be the principal, r is always going to be the rate as a decimal for a percentage. So as a for instance, if they give you 5%, you're going to change that to 0.05, and then n is the number of compounds, t is the time unit. And when I say number of compounds, if something is compounded weekly, it's compounded 52 times a year. If it's compounded daily, it's 365 times a year. Let's quickly review some of the properties of exponents. We haven't done that yet this semester, so just a quick review will probably be helpful, and I'm not going to prove any of these. I'm just going to give you a quick little example so you can see what it means. And so as a for instance, we start here. If I have x to the a times x to the b, the bases are the same. When I multiply those two exponentials, I add the exponents. So if I had x to the second times x to the third, that would be x to the fifth. If I divide two exponentials with the same base, I can subtract the exponents. So if I did x to the fourth over x squared, that would give me x. 4 minus 2 is 2. And then if I take a power to a power, if I raise an exponential to a power, then I'm going to multiply the two exponents. So if I have x squared to the fourth power, 2 times 4 is 8, I've got x to the 8th. If I have a fraction that I raise to a power, I can raise the numerator to that power and the denominator to that power. So as a for instance, if I have x over 3 squared, I could go x squared over 3 squared, and that I should simplify to x squared over 9. If I take a product to a power, I take each of the elements in that product to a power, and then I multiply. So 3x squared would be 3 squared x squared, which I would give as 9x squared. And then finally, radicals can be written as rational exponents. And so if I have the bth root of x to the a or the bth root of x all to the a power, that can be rewritten as a fractional exponent, a over b. Just as an example, the third root of x to the fourth can be written as x to the 4 over 3. All right. Let's talk a little bit about the asymptote of an exponential function, barring significant transformations. The general exponential function has a horizontal asymptote at y equals 0 as x approaches negative infinity. So let's go back up to that first picture. And this says as x goes to negative infinity, this function is going to tend to look like the x-axis. Now, that's pretty straightforward if we remember that a to the negative x is the same as 1 over a to the x as a positive. So what happens when x gets negative? Let's talk about that real quick. Let's use, as a for instance, 2. So we want to know what 2 to the 0, 2 to the negative 1, 2 to the negative 2 is. But let's work with pattern. I know what 2 to the first is, it's 2. I know what 2 squared is, it's 4. I know what 2 to the third is, it's 8. I know what 2 to the fourth is, it's 16. That should be enough. When I go from left to right, every time I move up, I go 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So that pattern is going to continue as I continue to go right. But there is another pattern that goes to the left, and it has to work as well. If I go 16 divided by 8, I get 2. If I go 8 divided by 4, I get 2. If I get 4 divided by 2, I get 2. So that pattern should continue as I go to the left. 2 divided by 2 is 1, and that's why anything to the 0 is 1. And then 1 divided by 2 is a half, and then a half divided by 2 is a fourth. Well, we can see that 1/4 is 1 over 2 squared. So this rule that we stated at the beginning does work. But what happens to these values as I go further to the left? Well, this will be 1 over 8. This will be 1 over 16. But you'll notice the pattern is always going to have in the 1 in the top, but the number in the bottom keeps getting bigger. For a fraction to be 0, I have to have 0 in the numerator. But if I use this rule, I will never get 0 in the numerator. I'll just keep getting smaller and smaller fractions that tend to go to 0. That's why I get this horizontal asymptote. Note, there is no vertical asymptote in the general form of an exponential function, even though you're going to see some exponential functions that go up very quickly. Alright, so even if you see something that looks like this as an exponential function, there is no vertical asymptote there. E, or Euler's number, is the base of the natural logarithm, a topic that we'll talk about later when we get to logarithms, the second part of this unit. And is an expression that often arises in the study of compound interest and continuous exponential growth. It can be calculated in multiple different ways. Below is the method relating to exponential growth. So when I say E, this letter and number, it is the limit, and I don't expect you to know what limit is, but if you're taking calculus next semester, we'll definitely get to it. as x goes to infinity. So as x goes to infinity, I get 1 plus 1 over x, all to the x power. Now, it seems if this number is tending to go to 0 as x gets much larger, then it would seem as if I would get 1 to a power, and that power becomes infinite. 1 to any value is just 1, but that's not how this ends up working. We do get this e value. So let's take a quick little Desmos break and talk about that number e. So here I have a function f of x equals 1 plus 1 over x to the x. And already by looking at the graph, it looks as if I have some sort of horizontal asymptote. But let's add in a table. And if I plug in 1, I get 2, and that makes sense because 1 plus 1 over 1 is 2. 2 to the first power would just be 2. And so let's just start plugging in larger and larger values. So if I plug in 10, I get 2.5. If I plug in 100, I get 2.7. 1,000, 2.71. 10,000, 2.718. 100,000, even to the thousands place, it's not changing anymore. And then let's just plug in 1,000,000. And we see that this number is starting to
Converge to a single value.
and you can see that the bigger this gets, the smaller the change. And so e is this limiting value. And Desmos doesn't have many values, but when you type in e, Desmos automatically assigns that. A lot of time when you type in just a letter, it'll want to do a slider. But in this case, e has a value, and it's 2.7162. Now, you should think of e the same way you think of pi. When you're dealing with circles, pi 3.14, you think of that number. When you're doing exponential growth, you should be thinking about e. Now, you're never going to need to memorize this number because anytime you're going to use it, it'll be with a calculator. But e is an irrational number that does have a value that Desmos uses. All right, let's talk about describing some transformations from the given graph. Here I see one transformation, and if I go back in there, I could say, okay, I've got f of x is
10 to the x.
That's going to be my parent function. If I'm adding 4 here, if I follow my order of operations, if I plug in a value, say x equals 5, what's the first thing that happens to it? I'm going to add 4 to it. So I'm adding to the variable before I do the exponent. That means that this is going to be a translation 4 units left. And again, we can see that in Desmos. There is f of x equals 10 to the x. If I type in g of x equal to 10 raised to, and in Desmos, when you type in more than just a single value for the exponent, you're going to want to plug it in parentheses, or else Desmos will push it back down into the main line. And we can see that we have a graph of exactly the same shape, except and you can see 0, 1 now becomes 4, 1, or negative 4, 1. So that point right there has been moved 4 units to the left. All right, this next expression, I have f of x equals 1/4 to the x power. And here I have g of x is equal to 1/4 negative x plus 2. I see 2 transformations. If I pick a random number, say x equal to 5, the first thing that happens is that the variable is made negative. That is going to be a reflection in the y-axis. And then this plus 2, after I've done the function, will be a translation 2 units up. And so let's just take a look at those real quick in Desmos. And so again, here we see the black curve, f of x equals 1/4 x, gives you this exponential decay. G of x equals 1/4 to the negative x plus 2, you'll see that the black line is reflected about the y-axis and then move 2 units up. Next, complete the table to determine the balance A for $2,500 invested at a rate of R for T years, compounded N times per year. And here they say that R is 6% and N is for 10 years. For these first 5 values, I am going to use A equals P times 1 plus R all over N to the NT. And then for the continuous growth, I'm going to use that continuous growth function A equals PE to the RT. And anytime you have to do multiple calculations, we're just going to make a table.
Let's fill in the formulas with the given information.
And then go back to Desmos. So we will have A is equal to, our principal is 2,500. We have 1 plus our rate is 6%, so we'll change that to 0.06. It is number of compounds. That's going to be the thing that's changing. So when we go to Desmos, we're going to call that X. And then finally, we'll have X, and we know what the time unit is. It's 10, so we have a 10 there. And I'll probably rewrite it as 10x when we go to the example. Now for continuous growth, we know everything. It's A equals the principal $2,500 times E, which is a value that Desmos knows, at 0.06 as our rate times 10 as our time. I have no variables on this, so that thing I'm just going to calculate. Let's go back to Desmos. And so here we have our function, and it's not going to show up in the graph because the y-intercept is 2,500, so we're not going to look at it because that's not what we're looking for. We're going to make a table, so I'll add a table, and then I will change my y1 into f of x1, and then anything I plug in for x will come up. So they wanted simple interest is 1 time, and then they wanted 2 times a year, so semi-annually, and then 4 times a year, so quarterly, and then 12 times a year, so monthly, and then 365, so daily. And you'll notice, even though we're compounding this interest more and more, the amount of money for over 10 years is not going up. So in the course of 10 years, the difference between simple interest and interest that is compounded daily ends up being less than $100 over the course of 10 years. So that's not much. Even when we do continuous growth. So when I go 2,500 times E raised to 0.06 times 10, continuous compounding every instant of every moment of every second of every day of every month of the entire year for 10 years, the difference between compounded daily and compounded continuously is approximately 12 cents. So that's not a whole lot. So the number of compounds isn't necessarily the biggest deal in the world. Clearly, more money is better than less, but it's not a huge difference. And so I would fill in that table with all those values. Final question. Let Q represent a mass in grams of radioactive radium whose half-life is 1,600 years. The quantity of radium present after T years is given by this general exponential function, and this one's a little bit different. Here is my y, here is my a, the half is the b, and then the exponent is t over 1,600. It says determine the initial quantity when t is equal to 0. So if I'm doing part A, this one we can do in our head, because if I plug in 0, 0 divided by 1,600 is 0. Anything to the 0 power is 1. 1 times 25 is 25. So reading our units, we're talking about grams. So here I have 25 grams as my initial amount. It says determine the quantity after 1,000 years. And then part C asks us to use the graphing calculator to graph the function from 0 to 5,000. So let's do both of those at the same time. Now again, we don't see anything, but we know that it has a y-intercept of 25. So when I go to my little wrench here, I want to change the y-axis, the top y value, to 30. And you'll notice it looks as if it's almost a straight line. And that's okay, because Half-Life takes a long time. In this instance, it takes 1600 years for us to get half of 25. So this thing is going down so slowly that it takes 1600 just to get down to 12 and a half. They do ask us to graph this over 5,000. So we're going to make the x value 6,000 just so we can see the whole curve. And now that we do have a much larger scale on the x-axis, we can see that it does go down. And it wants us to determine the quantity after 1,000 years. We can do that a couple of different ways. We can go right to 1,000 and put our, see if we can get it on 1,000. So after 1,000 years, there's 16.21 grams left. And if we wanted to get a little bit closer than that, what we could do is we could go f of 1,000 and 16.204. So if I plug in put a 0, so if I put a 0 there, I'll have it accurate to 3 decimal places. We've done the graph. Will the quantity of radium ever be 0 grams? Explain. Well, this function has 0 as its horizontal asymptote. So the model will never go to 0. But in the real world, at some point in time, way in the future, you will have had only 1 atom of radium left, and then it will eventually break down as well. So according to the model, there will never be 0 grams of radium. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day: in an early draft of Episode 6, Return of the Jedi, Wookiees were to be the species of the forest moon of Endor. But since Chewbacca was technologically literate and could fly a starship, it didn't make sense for the Wookiees to be backwards and in the trees. Therefore, those Wookiees were replaced with lovable Ewoks. That's all I got for today, folks. Have a good day. Goodbye.